If it saturates, means that there is no further possibility of any further correlation, increase in correlation. So entropy is a function of the scale.
Okay.
Right? This is the thing. And with regard to your comment regarding the physics, we are not here to say that physics is doing something very extraordinary, and in economics it is not done. The idea is
physics versus economics.
So idea is to just put in a kind of a measure so that people get familiar with at least some terminology and all. Like me, I am learning a lot.
This one saying from 1970.
So that is the kind of a thing. So there are a whole lot of work. There is a whole subject called econophysics. Started with this term was used by Stanley, who is a statistical physics person.
There's a journal also.
There is a journal now also.
Econophysics journal is there.
Maybe have the next presentation. Yes.
No, the objective of knowledge sharing can result in heat and light both.
Yeah.
And so there can be no light without heat.
Yeah.
So heat is important. Heated discussions are always interesting. Otherwise, this becomes a National Development Council meeting, but when everybody makes a point and gets a clap and sits. And this is not a National Development Council meeting. Ideas have to be there. Otherwise, ideology is not there. And each discipline has its own ethos and history, and so they will get reflected. The whole idea of sharing is this.
Right. So good morning, everyone. Once again, the session is for the econophysics, and what we have conceptualized here is that we have a model given by Chen, which Professor Das has discussed in detail. So the behavior of this particular model, if we can simulate or regenerate or forecast using the machine learning approach. So basically, we have used the deep learning method here, and the method is basically eco-state network, which is derived from recurrent neural networks. So this is the paper, forecasting and regeneration of behavior of a time-delayed exponential system using the eco-state network. So if we go behind how this model was evolved by Chen. So study examines the two attractive characteristics, which are the memory and the chaos in simulation of a financial system. The magnitude of financial variable such as forex exchange rate, gross domestic product, interest rate, production, and the stock market prices can have the very long memory. So in fact, the correlation overlap with the longest time scale in the financial market, which was analyzed by Chen. So this means that all the fluctuations in the financial variables are correlated with all future fluctuations. So this was the idea. So the motivation for describing the financial system using a nonlinear model. So I have taken the Chen model, and it is the simultaneous process which have the memory and the chaos together. So this is the outline. I will be discussing on these terms. So what is the problem statement here is that the financial model exhibit or the mimic the characteristics of a dynamical system, and that follows some chaotic properties. So the model which Chen has discussed is basically having two different properties. One is the regular mode and one is the irregular chaotic mode. So we will see how it switches from the regular to irregular modes. Then we will attempt to forecast any multivariate dynamical chaotic system, and which is difficult for various machine learning algorithms, basically for the linear algorithm. So we will be working upon some dense networks. A huge number of neurons are involved in this, basically mimicking the human brain or child's brain. And then we have some training and test data which are generated by the dynamical system itself. So this is the financial system which is under study. So we have the quantity X, which represent the interest rate, Y represent the investment demand, Z is the price index, S is selling amount, C is cost per investment, is the elasticity of demand in commercial market. So this one on the left hand side is the chaotic model, and this is the time delay exponential model, which basically mimics some regular behavior after introducing few more feedback strength here. So any financial system, we have composed of three first order differential equations and the model under study here. And these are basically interest rate, investment demand, and the price index. The factor that influence the change in X, basically the interest rate, mainly comes from two aspects. First is the contradictions from the investment market, that is the surplus between investments and saving. And the second is structural adjustment from the goods prices. The changing in the rate of Y in production to the rate of investment and the proportion to the investment with the cost of investment and interest rate. Right. Similarly, Z is on the other hand controlled by the contradiction between supply and demand in commercial market. So these are the phase portrait which are shown by Professor Das also. So basically representing how this chaotic attractor is formed by the financial system. And if we plot a 3D graph here, so this is the 3D attractor by it. And if we plot the all time series here, so I have taken the data from 0 to say 7,000 points on the scale. Yeah. So these are two pictures. One is showing the bifurcation or the Hopf bifurcation diagram, another is the time series here. So here the point between before 4 and after 7 is basically the chaotic behavior, and in between 4 and 7 we have some regular behavior. So these are some parameters for the generating time series here. So this one here on the left hand side is basically the chaotic nature, and on the right hand side we have the regular behavior of the system. Now the eco-state network. So it's basically a reservoir computing approach. So what we do is we mimic a child spring here. In the center we have some neurons which are randomly connected. We try to feed some input into the system, and the system learns, or the neurons get adjusted, and after that we have some readout layer. So it follows the eco-state property. Basically the neurons change their states according to the input, and finally they settle onto a point where the memory has taken place, or the learning has taken place into the model. So this is the model here is, we have some input parameters here, or the input variables. We have this the portion which is a reservoir dense network. We may have more number of layers into it. Currently we have taken 400 dense layers here, and then finally we have some output here. We also have a feedback mechanism here from the learning rate. If some corrections are needed, so we can feedback the difference, and then again we can train the model in such a way that the difference between the expected output and the regenerated output is minimized. So here are the state change equations. Here basically we have the weightage of the input here, which is also multiplied with the time delay. Then we have the reservoir state here, the previous state, and the network weight here. Then we have the feedback quantity with respect to the error, and some noise factors are also included here. Again, this particular diagram represents the excitement of the neuron by the activation functions. When we feed some linear or non-linear activation functions, how the neuron behaves. So we have a different type of activation functions which can be used here. So in the current study, we have used two type of activation function. One is the Lagrange functions, a linear function, and other one is the tanh function, which is hyperbolic in nature. So non-linearity is there. So now two different aims are there for this study. One is the forecasting, and another one is regeneration. So what forecasting is basically comprised of most of sought after use case which involve forecasting of irregular capital market or financial system behavior. So in the entire system behavior, we need to predict the future state, right? So what we do is we fed some initial or the previous memory to the system that learns, and we stop the input to the system. Now this learned system is basically mimicking the what is it has learned, right? So like here in this graph, from 0 to 5,000 points I have kept for the learning, and there is a cutoff line here. And after this, there is no feeding into the network, and the network will forecast based upon the learning. Right. So in addition to the direct system forecasting, there may be practical situation where it is not required for to fully predict such nonlinear system. So basically, some states are predicted, regenerated basically, and at the time evolves, the regeneration efficiency drops because the memory is a very short-term memory here, and after the long, time interval, the memory fades away. So this is what it can be shown here. Another point in the regeneration is that we are correlating with some other dependent variable, like we have X, Y, and Z variables here. And what we are doing is that at certain point, we are feeding all the variables. And after that, we have lost or we have stopped 2 of the variables and only 1 is continuing, right? So based upon the correlation, the rest of the 2 will be regenerated by the system. So that means if it 3 variable system is there and 2 are stopped and 1 is continuing into the system, the rest 2 will be regenerated by the system, right? So we have 3 conditions here. One is the X driven approach. In this, we will regenerate Y and Z components, and similarly we have Y driven approach. That means Y will be continuing into the system and we will be regenerating X and Z components, right? And at the end, we have the Z components into the system and we will be regenerating X and Y components. Now, these are the state parameters of the eco-state network. So we have the reservoir dimension of 400 different layers and the neurons. Into it, we have 3 input dimensions here because we have X, Y, and Z parameter of the dynamical system. Then we set up few input density. That means how much part the input is playing into the forecasting of the regeneration. Then the radius reservoir density. That means basically how densely the networks of 400 layers are connected, whether they are sparsely connected or whether they are heavily connected into the network. Then we have some other parameters like leaking rate, normalization, and bias. And these are the results. In the forecasting, we have, as I talked earlier, that for slight time duration, it will be regenerating forecasting, and after that the memory will be fade away. So this blue line basically is showing the actual input which was to be generated or forecasted, and this red line here dotted is basically the response of the neural network. After some time it will be saturating or it will be decaying basically. So it happens for the upper layer. This top row is basically for the linear activation. So linear activation is not so much efficient for any nonlinear system. While in case of the tanh activation, basically the hyperbolic activation function, we can see that almost the similar mimicking of the system is there, right? So system is nonlinear and the activation function is nonlinear, right? And the system's efficiency here is increased for some duration. And if we talk about the regular behavior of the system, that means where the system is not into the chaotic state. So in the linear case, only X component is exactly reproduced and others are, Y is not so much reproduced. For few iterations, it was reproducing and then it decayed. But in X and Z condition, it is mimicking almost everything. And while in case of the nonlinear function like tanh activation, it is mimicking all the 3 components. Then for the chaotic state in the regeneration, where we are only feeding 1 variable into the system and other 2 are regenerated on the basis of correlation. So for the linear activation, we do not have any of regeneration in the X component, but Y is generated, right? Similarly, here the X is generated when Z is fed into the system and Y is not generated. But in case of the tanh activation, we can see that if we fed X into the system, Y and Z are regenerated. And if we fed Z into the system, then X and Y are regenerated 1 to 1. That means very less error are there. Similarly, for the regular behavior, all the components are regenerated because there is a heavy correlation between the input and the regenerated variables. Now, if we talk about the numbers here, so for the linear activations, we can see that it is having an error, but for non-linear activations, we have a very less scope of the error. So mean square error is very much, stabilized. And for the regeneration purpose, mean square error is very less for the non-linear activations in case of chaotic attractor, and in case of regular attractor for both linear and non-linear activations, we have very less error into the system. So this is how we can forecast and regenerate a system's behavior based upon the previous data. So 2 experiments were carried out for the TANH and the linear activation for regenerating and forecasting the behavior. So we can see that the financial system is forecasted as well as regenerated in different conditions, especially in input and activation functions. And it also shows the better performance for the TANH activation function as compared to the linear activation functions. We have also conducted study for different other activation functions like the wavelet functions and other activation functions we have used, and they have shown much prominent results and better than the TANH function. So basically, non-linear and hyperbolic and quadratic functions are behaving better activation functions as compared to the linear activation functions. So this is what the paper is. Thank you.
Observations, questions? Yes, please.
So actually, I had an observation, questions or clarifications for asking clarification from both Anandita as well as there are ARIMA models. Are you familiar with that? So how is because that also identifies a pattern, and even if it is non-stationary data, it will try to make it stationary by differencing if we mean non-stationary. If it is variance non-stationary, it will apply that box transformations and make it stationary. And finally, try to model using moving average and as well as autoregressive. Now, how did you compare the results that you got to how it is happening with ARIMA models, and did you find that yours is better than the regular ARIMA models?
Yeah, we have conducted various experiments. Like there are more statistical methods which are available for forecasting the time series, right? So this neural network approach is slightly different from that, and it behaves like the memory which is into the system, and then it tries to mimic that, right? So ANIMA and other techniques are more statistical, and this is more learning based approach. Right, so we have compared, and if for say my this study, we have seen that if we go for more dense layer for the neural network, that means we are providing them more, basically room for exploding the variables which are going into for the high dimension, and then we are reducing them at the prediction or the regeneration end, right? So that results is more better than the ARIMA and more different
But
models.
will it not be the case? See, you are adding more and more variables to it, but they may not be really explaining whatever phenomenon is happening. So in that case, is it not that you're modeling even the errors? Is it not over-identifying? Your model is not over-identifying whatever is happening. So maybe you're modeling even the error portions in that case. That is what, in general, what we learn is if we normal linear regression, if you keep on adding variables, it will say that it is perfect, 99% R square we will get. But then that doesn't mean that all those variables are relevant.
Yeah, so the purpose is please.
So that is how I was thinking. Because yes, neural networks means you will try to add as many of the variables that you want to put in order to identify the finally what the pattern looks like, right? And again, one more question was sudden, unpredicted thing. Can you really predict that? If that is possible, then definitely it is better than the existing animal models and all. Suppose, say, this COVID case, suddenly it has come up. Would it have?
You can't predict.
No, earlier past, looking at the past period.
Financial market crash. Can you predict if like a financial market crash?
I think
There are works where the models are there, which are, bankruptcies and all they are modeling, they're doing. And it has been successful for 200 such data they have taken, I've seen in a paper, and they predicted the bankruptcy, and it has happened. So I have seen, yeah.
And one more thing I would like to add here is, in neural network, we are not adding more parameters into the system or variable into the system. What we are doing is we are taking the data, the timeline of the data, we are feeding to the system, and we are letting the system to identify the variables which are contributing to it,
Yes.
right? And then on the basis of that, what will be the future behavior?
Yes. So
Right.
that means the past has to be something. what we
Right,
know,
some incidents
and
should be
should be-
recorded in the time series, then it can.
And it should be of the same type. I mean, sudden if something comes up from outside, which is not known, then your system will again. will
I
not
think
be able
it
to
depends on the time series. If some incidents are recorded into the time series, the system may,
predict.
I'm not sure, but system may predict.
Because it has not happened regularly, maybe it will not.
I just want to
consider-
add one point. I mean, autoregressive model, ARIMA model and all, we declare our independent variable and dependent variable. Whereas in deep learning, system look at the pattern of the overall data, and that's how by trial and error, system finds out the independent variable. We don't say that X is independent or Y is independent. So system first looks at the pattern of the data set, and then it identifies what can be the most successful independent variable, which can fetch the data pattern out of the whole set. So that is a basic difference between ARIMA and this deep learning.
Yes, sir.
Yeah, I have a clarification to Manish actually to this presentation. You use linear activation function and tangent activation function. So what I found in your linear activation function, initially the model was representing very well and then it faded away. It's not there in the 10H actually, or maybe you can use the sigmoid function and anyway probably not there. My question is why? Because there is no time element in the activation function. So why it has happened?
I think this is because of the limitation of the linear function, which
It has
basically.
to done through, if it is not representing the real data, it should represent not represent the real data from the time 0 to this. Why it is happening?
What happens in deep learning is the activation of the neurons happen based upon the activation functions, right? That activation basically triggers the learning experience, right?
There is no time element in activation. That's my question.
The timing element is there because you are feeding the data, and every data point has to go through the activation function. That it will be after that it will be going to the learning model. Before that, it has to go through the activation function. Huh? So that is why for each time variable here, for each point which is into the time domain, that has to go first to the activation function, and the output of the activation function is then be going towards the learning function, and then it will be predicting. So we have two different things here. One is the activation function at the input layer, and then activation function at the output layer, which is basically the sigmoid function. So that is why time is inbuilt in.
Can we have, would you like to summarize? Okay. Yeah.
Thank you everyone, and I would like to thank the organizers of the conference for including econophysics as a topic here. That is why we were able to.
Are you leaving? Are you leaving?
No, I'm not leaving. No, my time will be over. That's why. Thank you everyone.
After this speech, I want to make a statement on the whole methodology.
Sorry. A very good morning to everyone in this house. And today I will be presenting my presentation on how to model employment relations. Now, this is a very new thing that we have done, and it is an extension of basically mathematical sociological modeling. And there are various works by Sprott which shows that in love affair dynamics, delay does stabilize the affair. So if there are disputes. Now, we are here trying to do that. What is the dynamics of the employment relation? And here, the content that we will be going through in my presentation are basically the brief introduction, literature that is already there, mathematical model, the fixed point analysis, results and discussion, and conclusion. And this is the basically the schematic of the system that we are considering. Here there are three individuals. One is an employer represented by capital E. The employee is represented by a small e, and I is the intermediate, which is the yellow one. All of them have a tendency, all of them are belonging to a middle class, proper educated background, and we assume that they have tendencies of compromise, they have disappointment level, and they have disagreements or encounters between themselves. And with this, we come to the modeling part, but before that, I will highlight one literature, which is that by Nikolsky et al. And there in their study they found that employment relations, unlike industrial relations, are more focused on individual relations between the employee and the employer than the collective ones. And based on this, we have developed this model, which is completely interaction based model. It is not a database model, but a completely interaction based model, just like we have the predator prey models and other ecological models. Now, here there are different subset interaction systems. The first interaction system is between the employee and the employer. The second, which is from the perspective of the employee is not interacting directly with the intermediate colleague. Then the second one is the sub-interaction system of the employer, where he is interacting with both the employee and the intermediate colleague. The third one is of the intermediate colleague, which is again having an interaction, very indirect interaction based on the emotional status of the employer and the employee. And the last in the bottom is the composite system. Coming to the equations, X small e represents the emotional level of the employee, X capital E represents the emotional state of the employer, and Xi represents the emotional state of the intermediate colleague. All of them have the, as I have already mentioned, tendencies to compromise. They have disappointments and they have encounters. The encounter between the there are two encounters we are taking. One between the employee and the intermediate colleague, which is affecting positively to the employer emotional level, and secondly is the encounter between the employer and the employee, which is affecting your intermediate colleagues emotional level. Now, based on BAR 2004 model of a pluralist system, we have considered three components, which is equity, efficiency, and voice in our employment system. So basically, both the employer and the employee, and they are mature, they are educated, they hold self-esteem, they are confident in presenting their opinion with firmness, and they have sensitivities, adjustabilities, and intolerance. Along with that, they have an ideological ego. So this idealistic ego, basically, the idealistic ego here triggers the individual to be behaving more like an ideal person and showing more compromising in the relation. Now, based on that, the system has three fixed points, and these fixed points, we have found out the condition of the stability for each of the fixed points. Now, the first fixed point is the trivial solution where all the all the emotional states go to the zero level. Means the relationship ends basically between three of them in a emotional capacity we are speaking. And the second and the third, they are invariantly behaving and they represent the chaotic solutions. Now we have found out from the Raut's criteria the conditions of the stability for each of them. I will not go into detail of that, but basically we derive the characteristic equation, and from the characteristic equation we have that the E1, E2 and E3, three coefficients. Now E1 should be greater than 0, E3 should be greater than 0, and E1, E2 minus E3 should be greater than 0. Then the system is stable. Based on that, we have derived the condition of the disappointment coefficient at which the system will transit into the chaos, and the coefficients are further defined as the coefficient of compromise is dependent on the idealistic ego, the adjustability, the coefficient of disappointment is dependent on self-esteem, maturity and intolerance levels, and coefficient of encounter has its own weight. Now, how are we giving the values? The values are coming from this table where we have designed this table which is of the level of impact, and level 1 is of effect, that a particular disagreement or particular emotional state of the other individual is just affecting. Level 2 is that it is influencing you to behave according, it is influencing your mental state. You are right now not considering it, but affecting and then influence, and then it is that you are now considering. And the last level is of the action where it is getting converted, it is getting reflected in your actions. So accordingly we have assigned the weights depending on the combinations of these four levels, and we accordingly have the case 1, case 2 and case 3. And in case 1 we are having where basically in the disappointment coefficient it is the intolerance weight which is we are varying, and in the first case the intolerance is at the zero level. That means it is not even affecting, it is just not into the picture. Second case is when the intolerance is coming into the way, it just started affecting. And the last case is the worst scenario when it is getting converted into the actions. Okay, so of the individual. Now these are the three cases. The first case, which is the starting point of the relation where the intolerance factor is not there. So whatever is the disappointment level, we see that the system is stably existing in a spiral phase dynamics, and whatever initial point you start, after a particular point it just gets saturated. So the system is sustaining with a saturated level. In the next case, when our intolerance has started affecting, the situation comes in a limit cycle phase system. Limit cycle here represents that there is continuous transfer of dominance between the individuals in the relation. So sometimes someone is having more dominance, someone is having that time getting suppressed, and another time it is again changing, but it is happening in a periodic fashion, and there is a limit cycle kind of a system. Then in the last, when this disappointment is getting reflected into the actions of the individual, we see that there is a bound chaos happening. So then we find that from the bifurcation diagram also we have derived and we have validated the disappointment level that we earlier found from the Hertz from our fixed point analysis, that at what point the system will start moving towards the chaotic domain. And in the next bifurcation diagram, now earlier we considered equal level of disappointment for both the employee and the employer. in the extension of that study, what we did was that we considered unequal disappointment levels for the employee and the employer, and we see that when the employer is having your more what do you say that more disappointment level, higher disappointment level than the employee, then the system is getting the system is transiting into chaos early. Okay, while when the situation is vice versa, the system takes more time. So the main conclusion from all this study is that there is a critical value of the disappointment level which is associated, which leads you to the transition from stable to critical to the chaotic phase. And if the employee shows more constraint or more basically well-mannered behavior or more constraint on his disappointment level or doesn't allow it to get more into effect, then the relation remains stable. Now, a realistic example which is always asked, that what is the real life example of this? So the real life example of this in present office scenario, so you will not get recorded, but in Mahabharata it is very well recorded, and it is the simple system between Dhritarashtra, Vidur and Shakuni, where Shakuni is the intermediate, Vidur is the employee, and Dhritarashtra is the employer. And when the employer, which is Dhritarashtra, doesn't adhere to the advice of Vidura, and they are having more disappointment, the employer is having more disappointment, we transit into Mahabharata. In Mahabharata, the best part is that we see chaotic emotions between Vidur and Dhritarashtra, where when Dhritarashtra loses his son, Vidur is having a very passionate ground for Dhritarashtra, while when Dhritarashtra is asking, that is celebrating death of Abhimanyu, the same Vidura is criticizing him. So it's a chaotic state of emotion there.
Mahabharata is more complex than this complex.
Yeah.
We will not discuss that now.
No, that is a separate paper we are working on.
Yeah. I can discuss with you.
Yes, I think
But
that's.
there's a very interesting book, how difficult it is to be good.
That is a very idealistic
Yeah,
scenario.
Guru Charan Jha's book. That book is quite interesting. Have a look at, since you are working on it.
Yeah.
Guru Charan Jha's book is quite interesting. It talks about how complex the whole system is. Much more complex than our price system. So,
Have you finished?
Yeah,
Yeah, thanks very much. Yes.
yeah.
Mahabharata we will discuss later on.
Now, this is end of the.
Actually, I am very happy that you talked of limit cycle and all that. I mean, this reminds me of the time when I was doing the mathematical economics course. Of course, I wanted to give some story, but I think we don't have time. The 2 points I want to make. One point is, first I'll talk about the employment, and I'll go back to the share market. The employment, one area where this type of dynamics that you've shown could be applicable is when there is an employer is deciding between a network where he can have directly employed person or employed through contractor. So in the office, there is a contractor, there is a person who the contractor has brought, and because the contractor has brought that person, he will ensure that there is always good relation between the employer and the contract worker. But the other fellow, who is the regular worker, he can always create a lot of trouble. And actually, the employer is bringing through the contractor to teach a lesson to that regular fellow. Now, in this network, there are 4 bodies, 4 persons. This is actually applicable because why so many firms have contract workers, so many firms don't have contract, they don't like it. Because this system of having an intermediate and a person coming through the intermediate, they don't like this system. So you can therefore have an equilibrium where only 2 persons are existing, the contractor and his person is gone. About 60% of the firms. And 40% of the firms, they are coexisting. So I just saw one immediate application of this, and it will also help us in understanding why the over time more and more contractualization is happening in the industries. The second point is about the stock market. The stock market, we always thought the share price of any company today is the discounted value of the future stream of income that the company can earn. So if it is the future stream of income, and that from that comes the event study methodology, because the day an information comes that such company's green rating is 0, this is an added information in the hands of the buyer. He knows that the future stream of income is gone down. Now, in this machine learning, where is the future stream of income, or is it that it is already being built that every data point is already thinking about the future stream of income that is sort of concealed or combined into that information which it is learning?
Yes, of course.
But it is not working.
It's on.
It's
It's on.
It's on. The light is not, oh, this
On the
light is
side.
on.
It's
That's
flickering.
right. The whole idea about this session is we have a way of thinking, economists. We have theory and we have methodology. The physicists have a different way of thinking. But the problems are the same. The problems are the same, but the methodology is different. So I want to clarify and understand myself the similarities and differences. So that you don't want to be judgmental and say we are right and you are wrong. In that case, there's no discussion. And there's no learning also. And there's no sharing either. Basic point is you change system is non-linear and it has its consequences. And you don't say this is a dependent variable, this is an independent variable to start with. Just data close up. You are not saying that one. The methodology which most economists follow, I think continue to follow. We have a theory, or you develop a theory. Then from the theory, you deduce a hypothesis. Then to test that hypothesis, you look for data, and then you test it. But this artificial intelligence, big data analysis, but to a large extent, econophysics, puts the diagram upside down. You look at the data first. Don't look at it from the point of view of your theory, because you are preconceived. The theory, you have preconceived theory with a hypothesis. So you look for data which will support your hypothesis. But that is not science. So you look at it with an open eye rather than with a colored glass of your theory. And so when you look at it with open eye, then your data throws up some solutions. She clearly said we don't identify dependent and independent variable. Data shows up the complexity of the system. And then you have a conclusion, all of you. And then if you want to theorize, you theorize, or you don't theorize. Now that is where there's a turmoil. Because our system is from theory to testing. And your system is, we have no preconceived notions of theory at all. We look at the data and big data throws up. And maybe few decades ago it was not possible because the computation techniques were not there. So we kept quiet. But once the computation techniques have come, you are able to do that. If this is the basic difference between the economist's way of looking and your way of looking, this difference will contribute to kind of a, I won't say chaos, a kind of a turmoil. Because our way of looking at it from theory to data, your way of looking at it from data to the data itself throws up. And that's very interesting. And I'm trying to understand myself, this is the basic difference. If this difference is there, it will create a turmoil to both actually. So there should be more interaction so that we can meet. But I would like to know whether my understanding is totally wrong.
Well,
I mean, I think this is a very interesting topic. I could have also taken time on it. I will not. You are almost right. Almost right in your understanding. But yes, let us hear another comment.
Actually, this is precisely my point that I was talking to Shamba. In fact, this big data analysis, I mean, 2 years ago, I don't know what is it now, 2 years ago, someone in our department at Copenhagen Business School started doing it. And the management did not recognize that as academic activity. They actually considered that as commercial activity. So they asked the person to leave. And then that person actually started his own company, where he was actually providing, those services to them because they require, companies require this. So they collect this Google and all that. Sorry, I'm so much in that. So actually these companies, they are compiling all the data, that how the Google works. The moment you search anything, they will start showing those pictures to you. So, so these companies actually require this kind of knowledge and they are looking for such services. So in our department, this was not allowed to, this lady was not, it was not he actually, it was she was not allowed to continue with that. So this is how, I mean, this may be now changed, I don't know, but this was 2 years ago.
That's a mindset, so.
Can I come back?
Precisely,
Yes,
this is what it was, that economics is about theory.
No, I'll get to it further. This is not all about theory. In certain cases, they are theory. From theory, there's some testing. But there's a lot of cases we find the facts. This is the pattern, and then think what could be theory. I give an example. The inverse relationship between agricultural plot size and productivity.
Yes.
There is no theory. It was first found, and then people started thinking. What is the reason? What is the reason? There are many things like, I can give examples. So it is not necessary that we have to always start with theory. I think now 50% is maybe theory to testing, 50% is first finding the empirical pattern and going back to your desk and finding and thinking what could have caused this pattern.
Actually, there are two approaches to research. This is what I was talking yesterday also. One is deductive approach and one is inductive approach. Deductive approach is about the theory and then testing. Inductive approach is about finding the pattern and then deduce. And then you present the theory. Now, how far this approach is inductive,
tested and validated by the
that is not, because it only shows that it only shows the pattern that this person is going to see this. But how relevant it can lead to the theory formation, that is what the question is. So it is not that we are always doing deductive approach. Inductive approach is as much economic as economic research as deductive. But the only thing is that this machine learning, how far it leads to.
I'm sorry, I'll have to intervene because this is something.
I just want to add to this. The moment you developed a theory, it has become irrelevant because things have changed.
Okay, I think I will request, if possible, a tea session or an evening session where we can discuss this, because I have very simple questions to what has been said, but let us hear.
I guess there's no point in binarizing induction, deduction. Quite medievalish, I would say.
Well, there is a
No, let me.
Let it complete.
See, philosophy of science, if you see, Thomas Kuhn, thereafter, it's very clear. Science is a behavioral activity. So, epistemology creation. There is even social epistemology creation.
Yes.
I can give you an example. There's a book written by, I think, what's his name, Guha and Professor Madhav Gadgil, Fished Land.
Okay.
What he says, there's a clear message. 7 trees, you count 7 trees in the forest. 7 also means 2 plus 3 plus 1 plus 1. It's called fragmented forest. But a consolidated forest and fragmented forest are different. Supposing there are pachyderms, elephants, they move. They'll have to move through human habitats. This is what's happening in Bandipur. And then you have to look for new epistemologies. So Professor Gadgil, it's very clear. He writes, You can't be a fundamental ornithologist or conservation scientist because it's a corner solution. It's also crucial to learn from pastoral societies and communities. This is very much applicable to economics. I think here what helps us is not much physics, it's biology, sociology, geography,
Exactly.
geology, environmental science. So physics is of help to an extent for, I think there is physics of utility, thermodynamics principles. That's one reason in the 1800s, people used equilibrium concept. And then when the Second World War happened, people from Eastern Europe migrated to US, who brought the concept of isomorphization. Then the general equilibrium emerged. Those days have gone. Wrong epistemologies and bad ontologies.
Well, thank you very much, but the reason is very simple. I will, trained as a physicist, frankly admit that all that we have today is because we have learned from social sciences. Otherwise, we would not have talked about it. Let's be very clear, all physicists would accept that our concern with these issues is because it came from sociologists and economists. Otherwise, we were happily doing whatever we were doing. So there's a lot of feedback,
Knowledge sharing.
all is sharing, and therefore
And not
this
knowledge
is a
imparting.
fantastic. My only thing is that there are few other colleagues who want to join in. Raise the questions in 1 minute, please.
Yeah, okay, I have just
We
two
have
points. One
a
is,
concluding session where these heated discussions can take place.
I request the president to wait for the concluding session. Yes, please.
okay, I have 2 points. One is, look, we have both inductive and deductive. This is the debate between, you put it historically, Descartes and Bacon. Bacon was the one who insisted that there has to be an inductive. So we have to combine the two. And what big data does is that we used to use a few number of cases to induce a relation and then test it. Big data allows you to do a large number of cases to see if there's a pattern. So the two are linked. Second, I would really suggest, as we are discussing this, we have another field from which we need to learn, and that is evolutionary theory. And if we can include in this manner a group of scientists who work on evolutionary theory in our next or whenever possible conference, it would really be of great help to economists to be able to link with evolution.
Thank you so very much. We always looking for new ideas.
Exactly.
And most welcome, yes, most welcome. I'm also supposed to be, we are supposed to be discussing, but I think we have triggered a lot of discussion. Thank you so much. It has been a fascinating session. Thank you so much, all the
When
speakers.
ideas come, it will be.
That's always the idea. It's very good. Thank you very much.
Thank you.
All of you.
Can I just
All
end
of
with
you.
one remark?
Yes.
Yes, please.
It is basically you are touching the ear of elephant and we are touching the leg, but we are all touching the elephant.
Well said, well said. Thank you so much, Mr. Jain and the team for.
Very interesting. This theory exists today because certain things existed.
Yes.
Yes,
If those things don't exist, this theory will have to go. Then something else will come. That came because these things again existed. So that theories are not permanent. They are impermanent. They change from time to time. So dynamics is the permanent thing. The permanent thing is dynamics.
Thank you. Thank you. I will just,
We'll break for.
thank you, we go have tea, and at some stage, the economists, and sociologists must tell me what is the conservation law. In physics, we have energy conservation. Maybe there is some law, but counterpart, I don't know.